Okay, thank you, Reiner, and thank you everyone for coming with us today to look at photochemistry in the troposphere and the Across project. I'm going to begin by talking a little bit about general issues related to atmospheric photochemistry and air quality, and what we understand about those issues today, and then transition to the Across project to describe how we want to examine a specific issue related to air quality and atmospheric chemistry, using Paris as a case study.
So sorry, Chris, to interrupt you. Can you maybe try to get closer to the mic or something? It's a bit muted a bit.
Okay, let's see what I can do about that. I can certainly turn up volume here. Okay. So before I begin, I'd just take a moment here to thank my colleagues, my collaborators in this project. There's a number of people that are involved in putting together this field campaign. That's kind of the heart of the study. And there's a number of people both at LISA but throughout France, and actually a few folks from elsewhere in Europe that are part of this project, and also to the funding agencies who've helped support various aspects of this project to be able for it to move along. So the Earth's atmosphere is interactive with the rest of the Earth system, and this comes about because there are emissions from the surface, both man-made and then also natural emissions. And the man-made emissions, of course, come from things like power production and mostly transportation, but also it's been recognized recently that personal care products also contribute significantly to VOC emissions from humans. The biosphere emits various kinds of compounds, including organic compounds that come from trees and other vegetation. And of course, we have emissions from volcanoes and from the ocean. And then those compounds go up into the atmosphere, are processed, and then eventually are deposited back at the surface. And this cycle then has an effect on the Earth's climate if the compounds that are present interact with radiation, and also can affect clouds because there's particle formation and alteration through these chemical processes, and I'll talk about that a little bit. So this is an attempt to kind of summarize tropospheric chemistry. There are compounds that are released from the surface, as I said, and here's an example of some compounds in the left box that included a number of gases, including volatile organic compounds. So that's a whole class of compounds. It includes sulfur compounds, nitrogen compounds, and it also includes primary particles, things that are they're particles when they're emitted. When these things are in the atmosphere, they are exposed to oxidants, and these include the hydroxyl radical, ozone, the NO3 radical, which is primarily an oxidant at night because it's rapidly photolyzed during the day, and also proxy radicals are intermediates in this oxidation chemistry, and it leads then to various kinds of products where these compounds are changed into other compounds, alkyl nitrates and proxy nitrates and inorganic acids. So these compounds that were relatively reduced become more and more oxidized and find themselves at the end of the chain as inorganic acids, and then various kinds of oxygenated organic compounds. This chemistry also makes ozone and particles as kind of secondary products or kind of byproducts of all this chemistry. So that's kind of the basic string of what happens with chemistry. Then these compounds that are formed can be photolized. They can be returned kind of back to the reactive pool, or they can be deposited at the surface. So this bottom box in the middle shows other processes that can happen. As I mentioned, there's deposition, but there's also photolysis. Some molecules absorb solar radiation and are broken apart and make atoms and radicals. We have to be aware that these chemical reactions have temperature and pressure dependence. Some of them. There's equilibrium involved. NO3 associates with NO2 to make N2O5, and so that affects the NO3 concentration that you're going to build up to. And then there's, in some instances, thermodynamics can play a role. And then aerosols that are formed can act as cloud condensation nuclei, and so affect the cloud abundance. And they also can interact with radiation through their optical properties. So let me show you just a few examples of this chemistry. So here's a couple of what would be anthropogenic compounds. So it's propane and a C5 alkene. So it's got one double bond. These compounds react with OH and they make proxy radicals. So there you can see the double oxygen. So that's the indicative of a proxy radical. And then that species can do a number of things: react with NO, react with NO3, react with HO2, and you make different products then depending on what pathway it takes. And this branching depends on the concentration of whatever the reactant is and the rate constant. And so you can make things like acetone here in this middle channel, or nitrates or other kinds of compounds, peroxides. And then in the case of the alkene, the OH could abstract a hydrogen like it did in the alkane, but often it adds to the double bond. And in this particular case, 65% of the time, it adds to the double bond in a particular spot and makes a different kind of proxy radical, a hydroxy proxy radical. And this can undergo that similar kind of chemistry, make similar kinds of compounds, carbonyl compounds, nitrates, peroxides, and so on. So that's kind of the basic kind of chemistry for alkanes and alkenes. Now, if we look at biogenic compounds, so alpha pinene is a terpene. It's a C10 compound that is emitted primarily by evergreen trees of a certain type. And when that compound is in the atmosphere, it has double bonds. Those double bond, well, it has one double bond. That double bond can react with ozone and lead to a number of compounds, but you can see over here on the right that we end up with proxy radicals. We end up with a C10H15O4 proxy radical of various kinds of structures depending on the pathway. And recently we've discovered that these proxy radicals can do this thing called oxidation, where they keep adding oxygen and they end up rapidly going from an O4, a molecule of 4 oxygens, to a molecule with maybe 7 or 8 or 10 oxygens, because there's a addition of oxygen and then a rearrangement, addition of oxygen and rearrangement. And this all happens very fast. And so this is a step that we didn't really have in our models until recently. This is kind of a relatively new finding, but it's important when we're talking about fairly large organic compounds. So if we're going to try to understand some aspect of atmospheric chemistry, there's various things we can do. We could take, say we want to understand the chemistry of one specific compound. We could take it into the laboratory and see how fast it reacts with OH, and see where it absorbs radiation to see if it photolizes. And we can do chamber studies where we either do one compound or a whole mixture of compounds and expose it to sunlight, a simulated sunlight, and kind of see what what kind of compounds it makes and what kind of particles it makes and so on. We can, alternatively, we can plan a field measurement campaign to examine a particular topic. And this might involve locations on the ground, maybe multiple locations. It might involve several kinds of platforms, perhaps balloons or airplanes or towers. And there's different kinds of approaches one could imagine, where you're either trying to follow the air or you let the air come by you, and you see how things evolve. And then numerical modeling is a way to kind of understand laboratory studies and field studies, but also to predict what's going on in the atmosphere. And there's a number of ways that can be done with different scales and different resolutions and different dimensions. And this can also be used for forecasting air quality, not just forecasting the weather. And in this case, the centerpiece of our across project is a field measurement campaign. It has some other aspects as well, and that include laboratory studies, but today I'm going to mostly focus on this field measurement campaign that we're in the planning stages for. So let me give you a few examples of some other, just quickly, some other field campaigns. Here's a campaign that took place in France, near Paris in 2010. This is called Megapoly. And on the plot on the left, you can see the kind of circle at the bottom. That's going around Paris. And then this is an airplane that did transects through the plume. So the reddish colors, reddish and yellow colors are the Paris plume that the instrument sampled from the aircraft platform. And in fact, these plots to the right show a number of different compounds. These are all aerosol quantities. So the organic component of aerosols, the nitrate component, sulfate component, and so on. And so the left column shows the measurements and the right column shows the model. And you've noticed the model isn't perfect, but it shows some similarities to the measurements, and those differences are useful because we can learn more about what we do and what we don't understand about what's going on in the atmosphere. Here's a couple other studies that involved aircraft. One was looking at, it was 7 campaigns between February and May, and the idea was to look at the evolution of ozone as winter changed to spring and into early summer. And so these allowed us to look at the evolution of ozone, and also allowed us to look at things like ozone depletion events, which happen in the polar regions in the springtime, where halogens come out of the snow and cause ozone depletion. So, and then on the right is a campaign looking at outflow from Asia, and this was 2 aircraft flying around trying to understand what was coming out of the Asian continent and how it was evolving as it moved downwind. And then finally, here's a number of studies that took place in the Southeast United States in 2013. The top plot is for 3 aircraft that were flying kind of in semi-coordination, looking at a number of issues. And then the bottom plots are 2 other aircraft. So there were 5 aircraft in all that were looking at atmospheric chemistry in the Southeast United States, which is an area that has a lot of urban regions, but also has forested areas as well. And then there's also some ground sites. These red plots show ground sites. So it was an area both of it was a studies that made use of aircraft and ground platforms. And then finally, here's one in Brazil, in the Amazon. Here's Manaus, and the red lines are a bunch of aircraft flights that took place in 2 intensive periods, looking at the evolution of this urban air as it mixes with the emissions from the forest. So very much like what we're trying to do with across. Now, one of the things that we need to be thinking about if we're comparing the present study to older campaigns is that the emissions from cities has changed over the last 15 years, 20 years. And generally this is for roadside composition. So this is roadside concentrations, and generally those have gone down for most substances at a number of cities, including Paris. And that includes things like carbon monoxide particles, less than 2.5 microns, NO2, SO2, BTEX is aromatic organic compounds. The one exception is ozone, that as these other concentrations of these other things have gone down, ozone has actually gone up within the city. This is kind of what you'd expect, because there is a kind of a quenching of ozone by oxides of nitrogen, and as the oxides of nitrogen go down, you kind of expect the ozone to go up. Often what we look at is the sum of ozone and NO2, because they tend to be kind of, that tends to be more conserved. So if we're going to compare 2010 to 2022, we need to be aware that the urban situation has changed. So what is across? This is kind of the motherhood statement. It's a framework for the exploration of atmospheric interactions of urban emissions and biogenic emissions. That's the short of it. And we're doing this through a field study. That's the main kind of center point of our project, but we also do some laboratory studies, and this is going to involve some clever data analysis using models and other tools to try to extract the information we want out of the measurements. And the goal is to improve chemical mechanisms. So these are the multi-step chemical reactions that each have a rate constant and each have specific reactants and products. And a model has a chemical mechanism that describes how all the species are made and destroyed as a function of temperature and pressure and time. And then eventually, we hope that this information can make us more, have higher quality air quality forecasts, and especially as the climate is changing and the temperatures are changing. So here's a kind of a schematic of what across looks like. Here's Paris on the left-hand side. So Paris has its emissions of VOCs and NOx and particles and soot, and those go up in the atmosphere, and sunlight shines on that air, and free radicals are made, and the processing of those emissions starts. If the wind is blowing in the right direction, it can encounter forests that are near Paris. And I'll show you a picture of that in just a moment. And these forests emit other kinds of compounds. They emit VOCs, but they're different kinds of VOCs. They're more like the alpha pinene and isoprene compounds, and they're different than benzene and pentane. And what we're interested in is how this chemistry of urban and this chemistry of biogenic is changed when these two air masses are mixed. And we're going to do that by making observations from a tower that's sitting in the forest. We're also going to make use of aircraft, and where we look at the evolution as this air mass moves downwind, and try to, from the measurements of the products and the intermediates that are present, we'll try to understand what this is telling us about these two what happens when these air masses mix. Let me describe what we think, some of the things we think might happen. This is a calculation of what happens with various kinds of proxy radicals. So proxy radicals are all those things that have an OO ending, and it's a radical, so it's very reactive. And then the other end is it starts out with hydrogen atoms and then a methyl group, and there's for every VOC in the atmosphere, there's a proxy radical, there's potentially a proxy radical, or several proxy radicals of different structures. So this shows the relative contribution of various reactions, various loss pathways versus NO, versus the nitric oxide concentration. So when the NO is low on the left-hand side of each of these plots, then most of the reactions are radical reactions. HO2 reacting with RO2, RO2, methyl 2 reacting with HO2. And so that leads to one kind of product. And then at higher NO, other kinds of reactions take over. Reactions between NO and NO2, between the radicals and NO2 or the radicals and NO, and that leads to other kinds of products. And of course, there's a transition in between where you kind of get both. And so we can imagine that when the NOx from an urban area mixes in with biogenic air, then the biogenic oxidation pathways are going to be slightly different, depending exactly how much regional NOx there is and how much this moves over to the right. We expect it to move over to the right as we're mixing in this urban air. The question is how far it moves to the right and where it was before that. But that's one effect that we expect. Here's a study that came out recently that shows secondary organic aerosol yields from alpha pinene. So you react alpha pinene as it does in the atmosphere in the laboratory, and you look at the mass of aerosol that is made from its oxidation. And then, so each one of these is a different experiment. And then what the researchers did was added isoprene, and they noticed that the yields of aerosol went down as they added isoprene. Now this, we don't know exactly what the mechanism is, but one possibility is that we're getting competition between isoprene and alpha pinene for the oxidant, and that is making, and the isoprene, when it grabs the oxidant, doesn't make as much aerosol. It actually makes much less aerosol than when alpha pinene is oxidized. So that kind of phenomenon is something that we might see. Here's a similar thing with toluene. That's an anthropogenic VOC. It's an aromatic compound, and and this shows the yields over here on the very right. It's the yields in percent. So this is the ratio, basically expressed as a percent of the mass of aerosol divided by the mass of toluene that has been reacted, and it's shown versus NOx. And you can see that at first NOx causes an increase in the aerosol yield, and then it causes a decrease. And it also changes the properties of the aerosol. There's a larger number of aerosols at higher NOx, at least up to the middle point, and the diameter of these aerosols are bigger. So that's an interesting finding, and that affects then the optical properties and stuff. Now these NOx levels are quite high. This is almost 200 parts per billion, which Paris is going to be more over here in the left-hand side of the plot. But still, this is the kind of thing that we think we might see. So here's a kind of a summary of what across is all about in a kind of a map sense. If you look in the upper right, there's a map of France, and there's a black square around Paris, and that's the across study area. It's about 100 kilometers in all directions from Paris. And in the lower left, the bigger white plot shows a number of parts of components of across. There's a brown kind of outline that shows the Paris urban area. The lighter orange outline is basically the city of Paris, and there's green outlines. These are forested areas, national parks, basically around Paris. They're all around Paris, as you can see. And then these dots are various ground sites that we're going to use. There's the teal triangles are at the Paris region, Ile-de-France Air Quality Network. There's a pink triangle that shows one station of the air quality network that's farther south. And there's also a station in Orléans. We're building a super site, basically, in the Rambouillet Forest. That's the red square, and there's a tower there that we're going to make use of. And we're going to put down a number of instruments that are either going to sample from the top of the tower or from a manifold that will bring air down to instruments on the ground. And then there's the site called CERTA. This is a site that's existed for some time that makes all kinds of measurements of atmospheric composition as well as meteorological variables. And they're going to be part of our, we're going to share data with CERTA. And then there's going to be a station in the Paris urban area at the University of Paris, where we're going to make a number of measurements. And then we're also going to have an aircraft. I'll talk a little bit more about that in a moment, but this little dotted pattern shows one type of flight pattern that one could imagine with the aircraft. I'll talk a little bit more about that in a second as well, about how we might fly the aircraft. So here's here's 3 of the sites with lists of compounds that we're going to measure. These are the same compounds I talked about earlier in the talk. Not oxides of nitrogen and VOCs and meteorology, aerosol composition and amount, ozone, and those same kind of measurements are going to take place at CERTA and also at our Rambouillet site, but also a number of additional measurements that include things like alkyl nitrates and proxy nitrates and acids. And so this measurement site will be a lot more comprehensive, and that will be kind of the focus of our analysis when combined with the other measurements that we're making also from the aircraft. So this is the ATR 42. It's part of the French aircraft fleet, and this is outfitted with again similar kinds of measurements that include, here's some of alkyl nitrates and proxy nitrates and ozone and aerosol composition and properties. And so these data will be very compatible with the data that we're taking on the ground. And we're going to fly the plane more than 50 hours over 15 or 16 flights. And the flights are about 3 to 3.5 hours. And so we'll probably fly in the afternoon when the photochemistry is very active and there's a lot going on. And this will give us a horizontal picture, a horizontal and vertical picture of what's going on. So here's one idea about how the aircraft might fly. The blue dot would be our base. We still haven't completely figured that out yet, but this is the candidate right now. And so the plane would fly down and get into a pattern that would have these little racetrack circles. And we picked that kind of pattern because there are some measurements that are very slow. There are filter samples that need to be integrated for quite some time. And so that allows integration over this racetrack, while the faster measurements can measure up and down these tracks, and we can get the concentration of various species as a function of downwind transport time or distance. And then the square, as before, is the Rambouillet Forest, and with this pattern we'll do circles around the tower site, so we can get good connection between the airborne and the ground measurements. And we will also likely do vertical profiles, so we'll measure the profile of species around in the neighborhood of the site. Now, if we take this is the same pattern, but it's just rotated around to different wind directions. So we can study different things this way. If you can imagine, say, a pattern that goes from the southeast to the northwest, that can measure mostly just biogenic chemistry, because the urban air won't be mixing over into the region. Here's Paris over here to the right. And so these are rotated. This pattern is rotated around the Rambouillet site. And so there's a number of different kinds of studies. We're only going to take 15 flights, so we aren't going to do all of these. But as the wind, we have to live by what the wind provides for us, and we can get some valuable information by looking at different wind directions. And then this is a similar kind of pattern. It doesn't have the little circle around the Rambouillet site. These are centered on Paris. And so the idea here would be we can look at urban air going downwind of Paris that either is not mixing with biogenic emissions, like the one that's going straight to the east, or ones that are going other directions that might be mixing with biogenic emissions. Okay, let me switch gears just a little bit. This is another aspect of the ACROSS project, and that is we acquired a chemical ionization time of flight mass spectrometer instrument, and with the idea to supplement our ability to measure oxygenated VOCs. And so let me just describe briefly what that looks like. We decided to use nitrate ions as the reagent ions. So we bring ambient air in and they react with nitrate ions, and then they make products that are unique to those to particular compounds that are in the atmosphere. And this is particularly sensitive to highly oxygenated compounds. So this plot in the lower left shows an analysis that Riva did that shows that the nitrate ionization is more suitable for oxygen levels in this is a terpene backbone. And once it gets about 4 oxygens, then the nitrate starts to be sensitive, where these other ionization schemes are more sensitive to other amounts of oxygen. So the way it works is if it's a strong acid, the nitrate will abstract the hydrogen and you'll make a different ion. If it's a weaker acid, you can make clusters. And we're in the process of learning what kinds of things make clusters. It's not necessarily even all acids. Other kinds of compounds can make clusters as well. And then these can be measured by their mass. And so that's how mass spectroscopy works. First, we make reagent ions in the inlet. Those, we put a charge on the walls of the flow tube, and that pushes the ions into the middle. They react with compounds in the sample, and then they're drawn into the mass spectrometer. And once in the mass spectrometer, they're formed into a beam that is maintained as the pressure is gradually reduced from ambient pressure down to 10⁻⁶ millibar. And at this pressure, we're essentially collision free. And then ions are pulsed out of that beam, and they undergo a path that then they are detected, and what is stored basically is the transit time from the time that they were pulsed until the time they arrived. And that is related to their mass. And we can figure out what that relationship is by calibrations. We have a number of species in there that we know their mass. And so that's basically how that works. And so here's oh my gosh, oh, there we go. Here's a sample mass spectrum. This is from a laboratory experiment with alpha pinene and ozone. The left-hand side shows our reagent ions. So there's NO3-, but you also get clusters of NO3- with nitric acid, because that nitric acid is in abundance because that we're using that to make the reagent ions. So you get these clusters of nitric acid. You also get a little bit of NO2- that comes about somehow. The way we make these ions is X-rays interact with gas phase nitric acid. And then the product ions, you see every one of these peaks is a different compound, or might be a whole collection of compounds with the same mass. And we've identified 4 of them in this analysis so far. And you can see that they're highly oxygenated, 7 to 9 or 9 oxygens in these 4 that we've identified. So this is going to be a really great tool for understanding or helping to try to understand the oxidation chemistry that's going on in the biogenic air masses and in the mixed biogenic urban air masses. So This is a description of kind of summary of what we're going to do and what we expect to learn. Across is a atmospheric study of mixed air masses. As I've said, we tend to employ state-of-the-art instrumentation for measuring as many species as we possibly can. And we're going to use the data to improve understanding, as I said before, using models and data analysis methods and so on. We hope that the information that we gather can be used to improve air quality models by improving the mechanism, and that might be adding reactions, it might be changing the products of a reaction. It can be any number of things. And then we hope to be able to answer the question: do forests near cities that emit biogenic compounds affect urban pollution? Do they affect the spread, the reach of urban pollution in the region? And then we're also interested in the products of this chemistry, like ozone and aerosols, on climate, because those have radiative effects that can affect climate and provide perhaps some kind of feedback, perhaps a positive kind of feedback. So I want to acknowledge, as I said earlier, the funders of this project. That includes 2 ANR grants. ANR is the kind of the agency that manages scientific research in France. But there are also some other agencies that have provided funding for the project, and we certainly appreciate that. So thank you for your attention. I'm happy to answer any questions anybody has.
Okay, thank you very much, Chris. That was very interesting. Yeah, everyone, you can either type questions on the question and answer tool or also in the chat, and I will then read them out. Or you can raise your hand, and then I will actually give you the opportunity to ask your question. Maybe first question from my side. That seems to be a huge logistical effort. You are like pulling together all the different grants and all that stuff. Must be huge work. When will you actually do the observation on the main campaign?
I didn't actually say that, but the project, the field campaign, the ground part of the field campaign is mid-June to almost the end of July. And then the aircraft part is shorter. It's mid-June to early July.
Okay, excellent.
So, but you're right. That's, I mean, my MOBCA project is a 5-year project, and I've spent 3.5 years so far. Now, granted, COVID and things were in here, but this is pulling all this together, writing proposals, finding partners, making plans, and it continues.
Mm-hmm. Okay. Any questions?
I said thank you, thank you, thank you for your thank you.
Okay. Yeah, maybe a question from my side again. It's there are so many reactions and interactions that you described that it seems like nearly impossible to like model or also to understand all these. Do you also envision employing deep learning approaches to dig through the data or things like that?
Yeah, I think that was hidden in my comment about clever data analysis procedures. So the lucky part is there's a lot of it we do understand. I mean, there are a lot of aspects of atmospheric chemistry that we do understand. A lot of the initial attack by hydroxyl radicals on organic compounds, we really know quite well. It's when you get farther down the chain where you're in the second and third and fourth step that things start to get more difficult. And that comes about partly because it's hard to study these third and fourth generation compounds because they're hard to make. They're hard to you basically need to synthesize some compound that's got 2 carbonyl groups and 7 hydroxyl groups and maybe a hydroperoxide on it. So that gets rather difficult. That's where these chamber studies can be really handy, where you can start with a compound and then try to model all the steps. Problem with chambers is they've got walls, and so there's the potential of interaction with the walls. But we think we know how to handle that as well. So I do believe that while you're right, it's a difficult. It's going to be difficult to fully extract information from this. I think we'll be able to tell if there's a big effect by mixing biogenic and anthropogenic air masses. If there's a big effect on the ozone production, that we'll be able to see it.
Mm-hmm. Okay, we have a question by Chen Wong. Please go ahead, Chen.
Yeah, hi, Chris. It's interesting. Just curious, why you didn't? My understanding from your presentation is aircraft measurements are limited to the basically summertime. Is that possible to arrange like a winter or deep fall? Because that's where the urban pollution looks like to have a somewhat different pathway, because there's a lot of haze actually occurred there. Although I would think the radical, all these rules might be slightly different than the summer. That might be helpful, but no. Well, I'm just random idea. I know this. Whatever you noted there is already. Then you just mentioned about chamber. Did you build out a chamber somewhere?
Yeah, we have a chamber at Lisa in Créteil.
Okay.
It's a 4 cubic meter stainless steel chamber.
Okay.
And it's part of that, what used to be Eurochamp 2020 is now Actrice. It's part of that network. And so, and it's really quite a very nice chamber.
Okay.
Let me briefly just address your first part.
Yeah.
One could imagine doing this experiment at different times of the year and learning different things, and that's definitely true. We decided that we would focus on an active photochemical time of the year, and that way the hope would be that the photochemistry is controlling. If you get into the fall and the winter, you get often you do see haze and stuff, but often it's just caused by physical processes. The photochemistry is slowed way down, and so it may not be as dramatic effect. Also, the biogenic emissions are temperature dependent, and they can be light dependent as well. And so that part of it would become a different project if we did it in the fall.
Yeah, I agree. Yeah, it's maybe a few additional chamber experiment. I mean, you have a few data anyway during different season. Could be useful to provide just a different pathway. I think it would my intuition is summer and the winter in the northern France could be very different, dramatically different. The chemistry there, yeah.
I agree.
Well,
okay, other questions? Maybe I have another one. How important do you think is Paris for the air quality in whole France? So more or less, how far does it reach, and or how far does the probably negative effect reach?
I think in a plume sense, you can get out to 100 kilometers pretty easily. But I think it's rare that it's more kind of general air pollution through the whole kind of Ile-de-France or wider. region. So, but we definitely observe this kind of regional pollution that's where all the pollution centers of Europe are kind of gathering together. So the Rhine Valley and Netherlands and Belgium and London, and they all kind of get together. And if the air is kind of stagnant, you can build up a kind of a pollution that covers the whole continent. So that can happen. When that happens, then Paris obviously is contributing their share to it as well. But when we really don't want to study that kind of situation. I think we'll learn a lot more if we have a situation where the wind is blowing and we're getting fresh urban emissions that are traveling in essentially one direction for a while, for a half a day. Then I think for what we want to accomplish with this study, that kind of situation is going to be better. But you don't get that all the time. There's no doubt about it. You definitely get kind of a regional pollution as well.
Okay. And okay, what do you think? As far as I get it, the impact of forests is mostly a positive one. That the volatile carbon compounds that they emit are having a good effect on the air chemistry. Is that correct?
I was very careful to not say what the sign was, whether it was positive or negative, because I don't know.
Okay.
I don't think we really know. We could find that we could find that forests in the region of cities causes air pollution to be more widespread. We could find the opposite. I don't know what we're going to find. I've been very careful to not be too predictive in that regard. We certainly could do some modeling and learn some things. We haven't gotten to that yet,
but the general human how to say perception or something that if you go into a forest and you actually have nice clean air, or that it's pleasant, that is maybe not what is above a forest, and when it interacts with city exhaust, so to say. So that's what you're saying.
Yeah, I mean, it could make different kinds of compounds. So maybe we make fewer carbonyl compounds when the urban pollution is present, but we make more nitrate compounds. And maybe the nitrates aren't as likely to go into the aerosol phase. So, maybe the particles maybe there's fewer particles. Or the particles don't grow as much. I mean, one could kind of put together scenarios where different kinds of things could happen. So, and part of it depends on it's kind of a competition for these various. I gave 3 or 4 possible kinds of things that could happen, but those things are in competition with each other, perhaps, and it's hard to get a gut feeling as to which one's going to win out.
So most of how it's modeled right now, or understood right now, what happens to city pollution is that it's diluted, and that you don't, or in models it's diluted and you don't have an effect whether it also reacts or how it reacts. The chemical mechanisms in regional models are highly parameterized, and the parameterization is based on chamber studies usually. And while they can put biogenic compounds in there, it may be that the parameterization isn't having them do the right thing. So it's not that they're doing nothing, but it may not be quite the right thing right now. And part of the problem is we need more computing power, so that we can put bigger chemical mechanisms into our regional models. Right now they only have 150 reactions or something. And it'd be nice if they had 10,000 reactions or something like that. Okay, then also get the problem of power. Yeah.